Okay. So, in today's class and a couple of lectures that follows, we will be talking about a topic called trajectory planning. What you have so far learned about various aspects of robotics is, say, different types of configurations of robotics that are used, different types of applications in which robots are used, different mechanisms that are used, the various elements that transmit motion from the individual joint actuators to the end effector that carries the tool that does the useful task for you in the first place. So, we have looked at various types of actuators and also the sensors that are integral part of any robot. Okay, so we have covered those aspects so far. In the current discussion, we will look at the trajectory planning. What we mean by trajectory planning and how we actually achieve it will consume us for the next couple of hours. If you look at a typical robot, you have probably looked at, say, a stationary robotic manipulator that essentially does a task of picking up objects, pick and place kind of a device. Supposing I have an object here, okay, I want to just pick it up and keep it here. This could be my task. Repeatedly I do it from, it could be from a stationary bin to another stationary place, or it could be on a moving conveyor from a material handling perspective. In this type of applications, you are actually looking at where the object is being picked up and where it is to be placed, and not really how is the exact specific path that the end effector traces in moving from point A to point B. Okay, so this is one type of applications for which a robot manipulator could be used. But this problem could be slightly more complicated when we talk in terms of, say, when you are moving from point A to point B, there is an obstacle in between. Okay, so you would like to go from point A to point B, but without it colliding with the obstacle. So therefore, you would like to specify probably as a user of the robot manipulator that, yes, look here, you need to go from point A to point B, but you would specify certain intermediate points, or what are known as via points, where you are not probably executing any specific task. You are probably not concerned if it exactly meets that point or it does not exactly go through that point, but you want to be approximately going through that point. Say, for example, here I can say that from point A I want to go to point B, but via a point C. So I want you to go roughly like this so that you avoid the obstacle. That is one way where I could specify a path indirectly through initial positions and final positions, but avoiding certain obstacles through what are known as via points. But in this whole process, the specific path taken between any 2 points is not of much significance. Okay, such points or such types of tasks, such types of motions are what are known as the point-to-point motions. So when we look at the broad issue of trajectory planning, we need to differentiate what are the different types of tasks a robot manipulator performs and how we generate these types of motions. So one category of motions is what is known as the pick and place or point-to-point type of motion. This is typical of say a material handling or an assembly type of robot. But on the other hand, supposing I am thinking of a robot manipulator which does welding on a complex automotive body shape. Okay, so the welding gun is held in the robot manipulator's end effector, and it has to follow, therefore, in this case, a specific contour where the 2 parts to be joined have to be welded together. So here, the specific path that is taken is of importance, not just the points, initial point and the final point, but the actual path through which the end effector tool moves through is also important. So these are known as continuous path type of motions. So we differentiate between these two different types of motions. One is the pick and place kind of motion where the specific path is not of importance. Other is the continuous path where the specific path through which the object is moving. For example, grinding operation. After the welding, you may want to grind the joint. Okay, so the grinding operations, these types of operations, the end effector's continuous movement along a path, specified path is desirable. So we need to look at how we can generate these types of motions. How do we plan for these type of motions? That will be the topic of discussion under the head trajectory planning. Now, when we look at this type of tasks, the gripper or end effector, which is at the tip of the robot manipulator, is actually doing the task for you, and therefore, and it operates in the real world coordinates, okay, in 3-dimensional space. So when you specify the task, it is natural for a user to specify it in terms of the motion of the end effector tip. If there are half a dozen joints which move this end effector in a coordinated manner, let that be so. But the user really says that the end effector tip should move in the 3-dimensional space in this particular way. Okay. So the natural way in which a robot system's user task specification happens is in terms of the 3D space of the end effector. Okay. So look at that aspect. So joint natural task specification, I would say task specification takes place in terms of the 3D space world coordinate frame. Okay. You are familiar with world coordinates and the tool coordinates, robot coordinates, and so on and so forth. So specifying it in terms of the 3D space in which the end effector operates, that is natural for the user. So if you want to achieve this kind of trajectory that the user specifies in terms of the end effector tip, considering the robot to be a closed loop feedback system, therefore if you have some way of sensing, okay, in the robotic manipulator, where you sense the end effector's position, its orientation. When I say that the end effector has to move through certain points, okay, we always keep in mind that it is not just a position, but it is the orientation in which it reaches that position, it is the velocity with which it moves through that point, or even the acceleration sometimes. Okay. So all these are implied when we talk in terms of the end effector's motion. So when your desired path or desired set of points and the motion through those points is specified by the user naturally in world coordinates, it is conceivable that you can have some external sensors which keep tracking the end effector's position, orientation, velocities, and so on and so forth, keep on feeding it into a closed loop feedback system, so that you will be able to achieve the kind of motion that you want to achieve. Okay. It is conceivable. So therefore, in such a case, the trajectory planning could entirely be done in terms of the motion of the end effector tip itself. But for any robotic manipulator, this is not a trivial task, even though it is something in principle you can think of a robotic manipulator with such external sensors that continuously monitor the end effector's position, orientation, velocity, and so on and so forth. It is not a trivial task to do this. What you have more commonly is that at each individual joint, each individual degree of freedom, an actuator which is actuating the degree of freedom will typically have a sensor, like for example the encoders that you have studied about. Okay. A typical rotary encoder could be mounted on a motor shaft that keeps tracking the angular position of the shaft. So you know by how much the motor shaft has been, that joint has moved through as a function of time. Or similarly, you could have a linear encoder that measures the position of a rectilinear motion continuously with respect to time. So for a prismatic joint. So it is more common that you have sensors at the individual joints rather than the end effector tip position. So in a closed loop feedback control system that the robot manipulator is, you look at a lower level control being achieved at each individual joint's motion rather than actually an end effector tip position. Okay. So the problem therefore will be that while it is natural for the task to be specified in terms of the end effector's world coordinates, it is convenient to achieve this through individual joints motion in a controlled coordinated manner. So you have to have this type of a mapping between the end effector's desired motion and the individual joints motion that I need to achieve, so that the end effector moves through that kind of a motion. So we talk in terms of world coordinates to joint space. need to be mapped. Okay, because one natural way to do it is in the world coordinates for the task to be specified, and the motion is in terms of each individual degree of freedom being actuated by an actuator with some sensors in a closed loop feedback system. So these two, it would be convenient if we can map them. Of course, these two are related, you are very familiar, these two are related through the kinematics of the particular configuration in which the robot manipulator is designed. Okay. So you could relate these two through the kinematics. Okay. When we say kinematics, we are looking at the geometric relationships between the motions of the individual joints through the linkages that are transmitting the motion from the individual joints to the end effector. Okay. So if we look at, for example, a simple planar 2R manipulator, say, okay. So you may have the xy coordinates, global xy coordinates. Okay. You look at a simple 2R manipulator. Okay. You want to relate the end effector's motion and the individual joints motion, say. Okay. This is a very simple example of a planar manipulator. So let me call this point as O and this point as A, and let this point be B. Okay. So let this link length be L1, let this link length AB be L2. Okay. And once you have designed the robotic manipulator, the link lengths L1 and L2 are known to you, and this is a 2 degree of freedom mechanism. So each joint motion, that is theta 1, theta 2. So joint space will consist of theta 1 and theta 2, and the workspace coordinates of the end effector will be in terms of x and y global Cartesian coordinates of the end effector tip. So xb, yb to theta 1, theta 2. So this is the kind of relationship that we need to establish and use in our trajectory planning. Okay. For this simple example is reasonably straightforward. We will see how the nature of the relations will be and what is the nature of the computation, so that we get a perspective on how we can plan the motion of the end effector in actual joint space. So for this particular example that we have taken, say you can write the x and y coordinates, which is reasonably straightforward through trigonometric relations. xb is L1 cos theta 1 plus L2 cos theta 2, and yb is L1 sin theta 1 plus L2 sin theta 2. Okay. Now look at these two simple relations. Okay. If you know how the joints are being moved, that means you know theta 1 and theta 2 at any instant of time. To calculate theta 1 and theta 2 being known, to calculate xb and yb is simple linear algebraic equations. Okay. In this particular case, it is a 2 by 2 set of equations. Given theta 1 and theta 2, L1 and L2 are already known because the robot manipulator's mechanism has been designed. So it is a simple 2 by 2 linear algebraic equation. So I would say that given theta 1, theta 2, to find xb, yb is linear algebraic equations. Okay. So this is the easier part. Now look at the other way around. That is, if I specify that the end effector's position be a given xb and yb, we need to find what should be the joint motions theta 1 and theta 2 at that instant of time, such that I get the tip to be at xb and yb. If you look at that in the reverse, so given xb and yb, what will be theta 1 and theta 2 that will achieve this position? Okay. So this is a trigonometric relation, therefore this will involve solution of nonlinear algebraic equations, okay, which could have consequent problems of multiple solutions. You may not have a explicit formula which computes theta 1, theta 2, etc. in general, multiple degrees of freedom of the mechanism in terms of the specified end effector's positions. You may have to use certain iterative solvers to come to theta 1, theta 2, theta 3, theta 4 and so on and so forth. Okay. So, given x b y b, to find theta 1, theta 2 is what is known as a nonlinear algebraic equation, slightly more complicated. Okay. Now, look at, we are not satisfied with only the position. So, look at now the velocities and acceleration space, how these coordinate relationships will get transformed. So, we differentiate these with respect to time, and automatically I will get the equations that relate the joint space velocities theta 1 dot, theta 2 dot with x b dot and y b dot, because when the end effector moves from point A to point B, I would require it to move with not only through the points, but also with certain specific velocities, okay, within a particular duration of time. Okay. So, I need to bring in that time into the equation. So, we need to look at how the velocities can be mapped. So, this is done simply by a process of differentiating these two equations with respect to time. So, let us see what those equations will look like. So, x b dot, for example, will be minus L 1 theta 1 dot sin theta 1 minus L 2 theta 2 dot sin theta 2. Y b dot is L 1 theta 1 dot cos theta 1 plus L 2 theta 2 dot cos theta 2. Or in general, if you want to capture it as a matrix equation, x b dot y b dot on one side, okay, you will have minus L 1 sin theta 1. I am using the abbreviated notation S for sin and C for cos, so that you get compact expressions, minus L 2 sin theta 2, L 1 cos theta 1 and L 2 cos theta 2 with the joint space coordinate velocities theta 1 dot and theta 2 dot. Okay. So, here again, if you look at the equation, the problem statement would be in this case in the following manner. I want the end effector tip or the robot manipulator joints to move through a particular position with certain velocity. So, the position information is already known when I talk in terms of velocity information. So, for a given position theta 1, theta 2 being known, if you are given theta 1 dot and theta 2 dot, to find x b dot y b dot is a straightforward again linear algebraic equation. Okay. Matrix multiplication will give you this x b dot and y b dot. Given x b dot and y b dot again, that is the end effector's velocity through a particular position. So, once you have specified a position, I am assuming that you have already solved the position problem for the joint space velocity positions. So, therefore, theta 1 and theta 2 are again known to you. So, given x b dot y b dot to be achieved at a particular position, determination of theta 1 dot theta 2 dot also is reasonably straightforward. You invert this matrix. So, if I call this as some C, okay. So, theta dots in general is C inverse x dot, where I am saying x dot to indicate the x and y components of the velocity of the end effector tip, and theta dot to indicate the all joint space velocities theta 1 dot, theta 2 dot and so on and so forth. Now, this matrix C is typically of this shape. Now, it is conceivable whenever you are thinking in terms of an inverse of a matrix, it is conceivable that the inverse may not exist. So, you could get into trouble. That all that it means is that the data that has been given in terms of the end effector's desired velocity at that position is not achievable, because the particular configuration of the mechanism may be that it is in a singular configuration. So, you cannot achieve any arbitrarily prescribed velocities in this particular position for the end effector, or there is no known solution for theta dot in terms of specified x dots, because the inverse of this does not exist. So, it means that it is in a singular position, for example. Okay. So, such problems could exist, but otherwise it is a fairly straightforward linear algebraic equation to be done. In the similar manner, you can differentiate these equations further. You will be able to relate the accelerations of the end effector tip that you want to the accelerations in terms of theta 1, theta 2 kind of joint variables. So, theta 1 double dot, theta 2 double dot, theta 1 dot. So, the acceleration problem would be that at a given position and velocity, you want to achieve certain accelerations. Therefore, position and velocities in the joint space as well as the Cartesian space of the end effector tip are assumed to be known, and you are trying to determine the joint space accelerations or the end effector tips accelerations. Okay. So, that problem also can be shown to be reasonably straightforward based on further differentiation of this equation. Okay. So, what we are really trying to say at this stage is therefore that even though we have given the example of a simple 2-hour manipulator, for any given robotic manipulator, once you know the kinematic configuration, once you know the link length and the types of joints, let it be prismatic joints or volute joints or whatever, once you know those, you can relate the joint space coordinates, generalized coordinates in joint space to the end effector's Cartesian motion. Okay. So, this background being there, we can think in terms of planning the end effector's motion in terms of the joint space motions. Okay. So, that is what we have we can summarize at this stage, that yes, even though I have certain required joint end effectors positions, velocities that I want to achieve, this can be done through a controlled coordinated motion of the individual joints, and I can start planning the trajectory in the joint space. Okay, fair enough. But when we look at joint space trajectory planning, that I do not look at now the end effectors, but if I look at the joint space trajectory planning in terms of theta 1 dot, theta 2 1, theta 2, theta 2 dot, and so on and so forth with respect to time, how I get these positions and velocities in terms of the joint coordinates, you could think in terms of couple of issues that come up before we go ahead actually do the planning and so on and so forth. Let us look at, for example, when you focus your attention primarily on the joint space, even though theta 1, theta 2, etc. vary in a particular manner with respect to time, say for example linearly with respect to time, it is not necessary that the end effector will move through a straight line in the Cartesian space. Okay. So, because of the nonlinear transformation relations, trigonometric relations that connect the joint space coordinates with the end effector's coordinates. So, we need to be wary of possible interferences, obstacles, collisions with obstacles that might happen amongst the links themselves or the links and end effector with the obstacles in the environment. We need to avoid those. Okay. So, this is one issue that we need to keep in mind. It is also possible, for example, that if you look at the joints with actuators of finite capabilities, even though we are now talking in terms of kinematic considerations only, planning the geometry of the motion, in a real physical system you have actuators at each of these joints with certain finite capabilities. So, therefore, the maximum acceleration that you can achieve for a joint may be specified. Okay. So, we will talk in terms of certain constraints coming from the joints, actuators and other considerations that will affect our planning. So, we look at, for example, what we call as the constraints joint constraints. So, maximum acceleration or the maximum torque that the actuator can exert. So, T max for example, and so on and so forth. Okay. So, these constraints actually come from the dynamics of the manipulator, okay, which is in real world operating in real conditions, okay, real joints, real actuators. So, therefore, certain finite capabilities, and so you will have certain constraints coming out of this. Okay. So, this is something we need to keep in mind when we plan our trajectories. Another constraint that could come, for example, from the same line of argument is that the kinematic relations that I have derived, I have written down just now, are assuming that the links are rigid. Okay. L1 and L2 are fixed parameters that were known once the 2-hour manipulator was designed, and in the motion of the manipulator in its workspace, the links are assumed to be rigid. But in actual practice, when you are talking in terms of very lightweight links, for example, for a manipulator used in space applications with very long booms as link lengths, with extending it to a couple of meters or more, and so on and so forth. So you are talking in terms of long links, okay, moving through the workspace at finite accelerations and decelerations. So inertia forces could set in vibrations in the system. The flexibilities at the joints in the links themselves, okay, could become various compliances could initiate vibrations in the system. So the end effector tip may not be at the position that you have determined through kinematic relationships based on rigid body, rigid links. Okay, flexibilities in the compliances in the joints and the links might affect your calculations. Okay, so that is another effect of the dynamics of the manipulator, apart from the maximum capabilities of the actuator itself and so on. So compliances will be another parameter that we need to look at. I am trying to highlight to you the various complexities involved in trajectory planning, so that we will get a total perspective before we jump into any particular planning scheme, so that you get the total perspective of the problem of trajectory planning. Okay, that is our aim at this stage. So you could have constraints on the joint motions from the maximum accelerations, or from the torques that can be exerted, or from the compliances, therefore flexibilities in the vibrations and so on and so forth. In any case, any non-smooth motion, even if the links are not compliant, any non-smooth, jerky, rough motion is undesirable, because it could set up vibrations. It could lead to quick wear and tear of various mechanism elements. So you want a certain type of constraints to be placed on the smoothness of motion. Okay, so we may have certain smoothness constraints. Okay. So you may want, say for example, velocity and acceleration to be continuous. Okay, that may be your specification. Okay, so smoothness of motion also becomes a particular a desired objective. So like this, you can list down different types of constraints. We have already looked at the Cartesian path constraints to avoid obstacles. Okay, so if you look at the overall problem, therefore, okay, of what comes under trajectory planning, if you are trying to achieve, say, from an initial position to a final position that is specified in, say, an optimal minimal time trajectory, if you want to plan, this could become therefore a complex, fairly formidable problem, optimization problem, in the sense of you have several constraints. One set of constraints could be in terms of the Cartesian space coordinates, because you know the obstacles positions, locations in the 3D space. So you could have constraints on the motions coming from the Cartesian space coordinates. You could have constraints on the individual joints capabilities and smoothness of motion constraints and so on, specified in terms of the joint variables. Okay, so you have mixed type of constraints and your governing equations and so on and so forth. So an optimization, a formal optimization problem for determining an optimal trajectory is not a trivial problem. Okay, you have similar and at the same time somewhat different type of problems that come up when we talk in terms of not fixed stationary robotic manipulators, but say for example a mobile robot, okay, like an AGV moving around on a shop floor. You may expect it to move around on a shop floor dynamically, avoiding obstacles which could be also moving and not stationary obstacles alone. So it has to dynamically do the path planning in certain minimal time or the least distance from point A to point B and so on and so forth. So the nature of the problems is even further accentuated there in terms of the mobile robot applications. So we will try to summarize and look at what actually is the trajectory planning problem. Therefore, if I specify that, so trajectory planning problem, therefore, if you look at that, I could state in the sense of move from initial position to final position via some intermediate points, because I may specify certain intermediate points also as a user, via some intermediate points and when I keep using the word points, always remember that it always implies the position, orientation, velocity, acceleration, whatever could be the set of motion variables that are associated with the motion of any typical object. So, in 3D space. So, you could ask this end effector also to move from initial position to a final position via some intermediate points within a specified duration of time, where you want control the speed and the accelerations that are achieved. So, within specified duration of time. Okay. Subject to some constraints like we just now discussed. Okay. Subject to constraints. And the nature of these constraints, as we have discussed, could be based on the individual joints motions in terms of the capabilities of the actuators and so on and so forth, in terms of the smoothness of motion that you want to be achieved, okay, depending on the task that you are doing, and depending on the manipulator dynamics itself, and obstacle avoidance type of constraints which are in the Cartesian space and so on and so forth. So, subjected to these various types of constraints, we want to be able to achieve this kind of a motion. Okay. So, this is the overall trajectory planning kind of a problem. Okay. So, let us look at now, while we talk about this overall trajectory planning problem for a robot, let us look at a specific individual joint, how I can move it from one position to another position. Okay. So, that we will do. But before we look at that, let us also remember another important issue in this, that I am trying to move it from one position to another position, final position, through certain points, but this is all a planned trajectory, okay, a planned set of motions. But the real motion is generated in real world in real time. Okay, this is all at the planning stage, which is offline essentially. Okay, the focus of our discussion is the planning problem offline. Okay, not essentially the dynamic real-time path planning type of problem. That is further more complicated. So, we are focusing our discussion on offline trajectory planning essentially. So, while we do some planning of the trajectory and the motions that we need to get with respect to time, the real actual generation of the motion takes place in real world when the robot manipulator operates as a closed loop feedback control system in 3D space in real constrained environments. Okay. So, due to the various aspects of the manipulator dynamics effects and interaction with environment effects and so on and so forth, your planned motion may not be achieved, and that is why you have various types of sensors that measure actually the motion that is achieved, and you have the closed loop feedback control systems that try to ensure that the planned motion is achieved as closely as possible. So, various types of control algorithms which will enable you to achieve this planned trajectory will be dealt with separately, okay, which are typically implemented both at the higher level and at the lower individual joint level. Various types of schemes are there. Those control algorithms will be discussed separately in another set of lectures. So, we are focusing primarily on the offline planning of our trajectories. Okay. Let us look at, for example, a simple single individual joint needs to be moved from one position to another position. Let us look at that type of a simple problem to begin with, to begin our discussion, because overall trajectory planning problem is what we have just now discussed. We like to do it in the what is known as the joint space planning. Joint space trajectory planning. Let us look at a single joint first, then we will worry about a manipulator which has several joints and so on. So, a single joint, say I will say single revolute joint to be more specific, but our discussion pertains to any type of joint. So, single revolute joint, okay. So, whose motion is say theta as a function of time. Okay. Now, you want to move it from one position to another position. That means, so initial position, say let us say that from position I would not say the initial or final position, I would just say consider that you want to move it from position I to position j, you want it to be moved. So, move from position I to position j. That means, specified theta I dot, theta I double dot in general, acceleration also could be specified, to position theta j, certain velocity theta j dot and certain acceleration theta j double dot, okay, in between 2 points. If you want to move from position I to position j and you want to plan a time and theta, so you have certain position here, okay, I, and you have certain position j. These could be initial and final positions, or these could be any two intermediate positions or via points. Okay. So, we take up general two positions I and j. Now, if you have prescribed theta I dot, theta I double dot here at this point and theta j dot, theta j double dot, what is a smooth trajectory between I and j that I need to use? How do I get that kind of a trajectory? That is the general question. Okay. Now, it may happen in particular instances that if these are initial and final positions, you may say that you are starting from rest. So, theta I dot, theta I double dot may be 0. You are placing the object which you have picked up from I at the final position j, and also you are reaching it at near 0 or 0 velocity. So, therefore, theta j dot, theta j double dot also could be 0. You may specify that, or okay, final position. So, or these could be intermediate positions or via points, as I said, and therefore, all these parameters could be non-zero in general. Okay. If we are able to analyze this problem, then we will see that the overall motion of the individual joints creating the final end effectors motion is a case of fitting a series of such points I, j, k, l, m, n, and so on and so forth. Okay. And each set of 2 points you can actually, or a set of points, the motion between them can be planned through a particular smooth trajectory that we generate using this type of an understanding, and you can use several such segments of motion to get the total motion from the initial configuration to the final configuration. Okay. So, that is the approach we are going to take, that I look at first how I will achieve a particular type of motion between 2 points I and j in a particular desired motion profile, and then see how I can use it for moving the actuators from initial position to the final configuration through a set of intermediate positions or whatever is the specified thing. So, let us look at this particular problem. It is easy to see that we are trying to actually find out the motion of the individual joint theta with respect to time. So, I define first, for the sake of convenience of the calculations and so on, I define a local time frame. when I say local time frame, it is local in the sense that it is for the duration of the motion between the 2 points I and j. So, tau varies. If Tij, let Tij be the time taken from I to j. Okay. So, therefore, my local time frame that I am defining, tau varies from 0 at the beginning of the motion, that is at position I, to Tij, okay, between any 2 points. So, my local time frame that I am going to use is tau, which varies from 0 to the time period between the time duration between any 2 points I and j given by Tij. So, therefore, the trajectory that I am trying to get would be a trajectory in terms of theta of tau. Now, what would be the trajectory that I would get? Okay, I need to plan for this. Okay. So, we could think in terms of a polynomial variation of theta with respect to time within this Ij, and the degree of the polynomial could be determined based on the number of constraints that you are placing. Okay. Because using these constraints, you are going to actually determine the coefficients in the linear polynomial that you are going to use. So, suppose you say that the initial position and initial velocity, I mean position at I, velocity at I, position at j and velocity at j are prescribed. Okay. So, in that case, you could have C naught plus C1 tau plus C2 tau squared plus C3 tau cube. Okay. In general, you are going to have actually a series of such terms, where you are going to use a linear polynomial, I mean you are going to use a polynomial curve fit, and the degree of the polynomial will be determined based on the number of coefficients you can determine. So, if you have 6 constraints, then you can determine 6 coefficients, and correspondingly you can fit an appropriate degree polynomial and so on and so forth. So, supposing you have the constraints as specified theta I dot, theta j dot. That means 4 coefficients can be determined because 4 constraints are specified, and so you can determine C naught, C1, C2, C3. So, you can determine you can do a cubic polynomial curve fit for the motion between the points I and j. Okay. If you have also prescribed accelerations, that means in the general case, if you have specified theta I dot, theta I double dot, theta j dot, theta j double dot. If you have the positions as velocities as well as acceleration specified, then the number of constraints are 6. So, therefore, 6 coefficients C naught to C1, C2, C3 up to C5 can be determined. Okay. So, you can fit an appropriate degree polynomial. Okay. So, C5 a tau power 5. So, you can go up to the 5th degree polynomial. If you have only position velocity, you can go up to only a cubic polynomial and so on and so forth. Okay. So, now let us look at the simpler case where only initial the I and j position and velocity are prescribed and accelerations are not usually specified. So, a case where theta I dot, theta j dot specified. Okay. That means I am talking about theta of tau is specifically C naught plus C1 tau plus C2 tau square C3 tau cube. Okay. So, now remember that the local time frame tau varies from 0 at the ith position to the time duration between the points Tij at the jth position. So, the constraints that I have on theta and theta dot can be written as theta of 0, that is the ith position, theta dot of 0 is theta I dot, theta corresponding to the time duration between the motion for the points T I j as theta j, theta dot corresponding to the motion end of the motion is theta dot j. Okay. So, we have 4 constraints and the 4 coefficients C01, C1, C2, C3 to be determined, which is readily done. So, if we look at the constraints, so theta I comes out to be simply C0, theta I dot will come out to be C1, because theta of tau is C0 plus C1 tau plus C2 tau squared C3 tau cube. Okay. So, theta dot of tau is C1 plus 2 C2 tau plus 3 C3 tau squared. So, therefore, at tau is equal to 0, you have theta is directly C0 and theta dot is directly C1. At the other end, theta j is C0 plus C1 Tij plus C2 Tij squared plus C3 Tij cube. And similarly, theta j dot is obtained by substituting tau is equal to Tij in the equation for the velocities here, and so theta dot j is C1 plus 2 C2 Tij plus 3 C3 Tij squared. Okay. So, I could call this equation 1, equation 2, equation 3 and equation 4. So, 4 equations to determine C0, C1, C2, C3. This can be generalized, as I said. I mean, if you have prescribed accelerations, that you can fit a higher degree polynomial, differentiate it for velocities, differentiate it for accelerations, and make the profile match the conditions prescribed at I and j. Okay. So, if you look at the cubic curve fit that we have got, the cubic curve fit that we just now achieved, it has certain simple advantages. It is the lowest degree polynomial that ensures the continuity of velocity and acceleration, because a cubic spline will ensure the velocities and accelerations up to second derivative continuity is guaranteed. So, it is the lowest degree polynomial that achieves this. Okay. And it is readily computed, as we have just now seen. So, it is one of the common spline interpolation schemes that is implemented in practice, cubic splines. So, if you look at, for example, for this type of a cubic spline strategy, the typical position variation with respect to time could be something like this. Okay. This is Tij, this is 0 time tau in the local coordinate frame between theta I and theta j. Okay. And corresponding time, your velocities would be something like this. This is Tij, this is Tij upon 2, 0. So, you have peak velocity here and you are moving like this. Okay. Your velocity profile for this type of cubic polynomial curve, it would look like this. Now, if you look at the how the accelerations will be for these type of cubic spline segments, then the accelerations that is theta double dot will be something like this. Tij, and the accelerations will actually move like this. Okay, accelerations will be linear, Tij upon 2 at the halfway point. It will cross to 0 where the peak velocity is, and then it will be deceleration phase after that. So, you will have this type of an acceleration profile. So, given any two positions I and j with prescribed velocities, you will be able to determine the coefficients C0, C1, C2, C3 for the cubic spline curve fit for the individual joints motion in this manner. Okay. Once you have got these coefficients, one given any value of Tij and the variable values theta dot theta, theta I, theta dot I, theta j dot, you will be able to compute this and actually generate the motion through the individual joints. Okay. So, this is feasible, but look at how it could be implemented in actual practice. If you have say n number of points through which you want the motion to be achieved, okay, in this type of strategy of doing the curve fitting, you are requiring that all the positions be specified and the velocities maybe in terms of the end effector's motion, and you can do the inverse kinematics to calculate through the kinematic relationships the joint space velocities. Okay, but somebody has to specify all the velocities at all the points. So, if you have say an initial position, okay, just imagine how this type of strategy will be implemented in actual practice, and then I have a final position where I need to go, and n points in between. Okay, between, so I have totally n plus 2 positions, and n plus 2 velocities have to be specified by the user, okay, at each of these positions. For this strategy to work, to be implemented in practice, then I need to specify, the user is required to specify, n plus 2 positions and velocities. Okay. So, in terms of trajectory planning, we now come up with another aspect of trajectory planning, that whatever strategy you do inside is internal to the manipulator. As far as the interface with the user is concerned, you need to have a way of specifying it in a simple manner. The user shouldn't have to be, shouldn't have to give huge amount of data. Okay, that is something we need to keep in mind. Another aspect that would come up when we are asking for such data from the user is that, as I have indicated in the kinematic relationships from the velocities in the joint space to the Cartesian space, the velocities that the user specifies at all the positions may not be achievable. Okay. So, the user not only has to give large data, but also has to give consistent data. Okay. So, in this particular strategy of specifying the trajectory planning, then we user need to give large data. That is one aspect. Okay. N plus 2 positions, he has to give the position and velocity information, but it has to be also kinematically consistent data, which is kinematically consistent. Okay. So, in terms of user interface, therefore, we come up to trajectory planning, we look at it in another angle, and then we add another constraint, so to say, which says that the user interface should be simple. Okay. So, another constraint, therefore, from the interface point of view, is that user interface must be simple. That is, we don't have to give complicated expressions, functions of time for the specification of the task, which is in world coordinates for him as a user as he sees it. Okay, he should be able to, in a simple manner, specify the task that needs to be done. That also throws up to the light that maybe many of the intermediate points, the via points, he doesn't really bother that the end effector tip exactly pass through those points. It could be approximately there, or even if it is exactly passing through those points, he may not really worry about what is the velocity with which the end effector tip moves through those points. Okay, it may be left to the system to calculate what could be an appropriate velocity to move through such a via point. Okay, so we will see how we can generalize this type of a strategy of trajectory planning in the next class for via points where velocities are not really specified. So the user simply says go from an initial position to a final position through these via points. Okay, so we will see the strategy of trajectory planning for those cases